Okay, so here in this video, we're going to go over the Gram-Schmidt process. So the idea here is that we want to build an orthogonal set. All right, now we want to start with a linearly independent set. All right, so let me switch over here and show what the process is in our textbook. Okay. All right, so here, this video, we're going to go in depth into this Gram-Schmidt procedure. So it states, suppose that S is equal to V1, V2, V3, up to Vp, is a linearly independent set of vectors in Cm. And now I want to define the vectors by this operation here, all right? So I arrive at a new set of vectors that I've redefined, calling them U1, U2, U3, U sub p. Then T is an orthogonal set of non-zero vectors, and the span of T is equal to the span of S. All right? So what it's telling me now, we don't mention non-zero vectors in S, but the fact that they're linearly independent is automatically telling me that they're non-zero. Okay, and through this process, we will not get a zero vector. So all these vectors will be non-zero, right? And their spans are going to be equal. What changes is that now instead of it just being linearly independent, it's linearly independent and orthogonal. Okay, all right. So here, let's a couple things here to figure out how this is going to work. So each step of the way, so this, you see we're subtracting a lot of different things here now. For the initial step, as we'll see, U1 will always equal V1. And then each additional vector, the next one will subtract this component U1, the next one will subtract another component, right? The idea here is, what we're doing is we're fixing on V1, that's going to be our starting point, right? And you can choose whichever one you want to be V1, right? Those are just chosen arbitrarily. And then from there, we're going to build this orthogonal set by, the reason why all those are subtraction is we're subtracting the components that are in the direction of this V sub 1, right? So we take our new vector, right? And we want to strip away anything that is in the direction of U sub 1, U sub 2, or whatever, all of the previous ones that came before it, right? So here, let's take a look at what this is going to look like in practice here, right? So the idea here is that when we're working with this Gram-Schmidt here, we have a vector here. Let's say two vectors, right? And then we'll generalize to more vectors here, right? There's some kind of projection onto this vector, let's say U, right? Part of this other vector V, let's call it V, right, is in the direction of U. So that procedure aims to like subtract all that out and essentially make it orthogonal, right? And then it does that if we add a third one, right? And if we're in R3, then you're subtracting each component that is in the direction of these other two, so that now you have the third one to be orthogonal to the previous two that came before it, right? And so forth, right? If we're in R4, the fourth one would subtract the components that are in that direction, right? So then you kind of force them, you're making them be orthogonal to each other, right? So let's start with a basic example here in R2. So let's say that V1 is equal to 2, 1, and V2 is equal to 1, 3. Okay, so these are linearly independent, right? We won't bother to do the check. I'll say we did the check already. They're linearly independent. So the Gram-Schmidt procedure, so I'll say GS procedure, starts off very easily. U1 is the first vector, so that doesn't change, right? That's kind of we start there. Okay, Now U2, we're going to subtract off, so we're going to have 1, 3, but now we're going to subtract everything from the previous vector to 1 that is in that direction, right? So that's where the U1, inner product of U1, V1, and U1, U1. All right, and the vector U1. Right, the norm of the vector, we divided out. Okay. Excuse me. All right, so we get 1, 3. This U1, V1 is going to be 5. And then U1, U1 is also going to be 5. And then the vector U1 is 2, 1. All right, so we just get 1 minus 2, which is -1, and 3 minus 1, which is 2. Okay, and now we have, you can verify that these are orthogonal, right? Interesting enough, right? If we think we're in R2, the plane, right? When we talk about perpendicular lines, negative reciprocal, right? And you could see that show up here. All right, so let's take a look here, just graphically what we're looking at. So we start off here, right? V1, V2, that's our set of linearly independent vectors, right? So there's two linearly independent, so they span the whole plane, right? And what the goal here is that we have our U1, which is the same as our V1, so that one remains unchanged. But then in the process here, in coming up with V2, again, we've stripped away, we subtracted away everything that was in the direction of our U1. And now we have this set of vectors here, which are orthogonal. All right. Now, in general, our kth vector U sub k, so the procedure to generalize it here, all right, U1 is always going to be V1. All right, now for each V sub k in the set, we want to subtract everything that is in the direction of all the previously constructed ones. So the way that's going to look is our U sub kth vector is going to be V sub k minus this sum here. All right. J goes from 1 to k minus 1. Uj V sub k over uj, which are all the previous ones, right? So if this is u2, then there's going to be only one term in this sum. If this is u3, there's going to be 2 terms in this sum that we're subtracting off, right? We're subtracting up all the previous ones, all of the projections that are in that direction. Okay. Okay. So let's take a look at an example. All right. And the output that we get, the vector is in the Gram-Schmidt procedure will be, give me the same span, right? As our linearly independent set. So let's say V1 is 1, 2, 1. V2 is 2, 1, 1. And then V3 is 1, 1, 3. Okay, and I want to apply the Gram-Schmidt procedure to come up with an orthogonal set. So the first step, U1 is V1. Okay, so that one is 1, 2, 1. All right. Now, U2 is going to be V2, but I'm going to subtract away, right, everything that's in the direction of my U1 from V2. So that requires to do this calculation, U1 V2 over the inner product of U1 U1, the vector U1. Okay, so I'll perform these calculations here, and this gives me 2, 1, 1. The inner product of U1 V2 is 5, and the inner product of U1 with U1 is going to be 6, and then U1 1, 2, 1. All right, and then doing this calculation, we get 7, 6 minus 4, 6, 1, 6, right? Now, I did skip a lot of calculations here, just kind of arithmetic, really, just the inner products I did on the side on my notes here. So it might be good practice to just kind of pause the video here and go through those calculations on your own so you could see where those numbers are coming from. Okay, now in order to simplify my calculations moving forward, I'm going to scale this vector, right? Scaling, I'm going to multiply by a scalar, so that really is not going to change the orthogonality of it, but it will simplify my calculation so I don't have to deal with too many fractions here. So U2, so I'm going to scale it. So I'm not going to choose this U2. It's going to be in that same direction, which is what I want, right? That's the important part. So scaled U2, I'm going to multiply through by 6, right? And that gives me 7, negative 4, 1. Oh, excuse me. Okay. Oh, man. Okay. Okay, so that is my scaled U2. So I've done the first two. Now for the third one. So we'll start with V3. And again, I want to subtract away everything that's in the direction of the previous ones that I created, U2 and U1. So the way I do that is by fixing on V3 and then taking inner products with U1. Over U1, U1. And then minus, so there'll be two components here. U2 V3 over U2 U2. That is U2. Okay, so then again, as before, you might want to stop here, right? Go back or do the calculations on your own here to just make sure that you are following along here. So this one is 1, 1, 3. Now this becomes, the top is 6. Numerator is also 6. And this is 1, 2, 1. And then here, the numerator here is 6. And the denominator here is 66. And then the vector here is 7, negative 4, 1. And you can see why it's advantageous to scale here, because if I had a fraction and another fraction, we could see how those start to get kind of out of hand here. So here, let's simplify this here. So this 1, 1, 3. That's 1. So 1, 2, 1. And then here, minus 1, 11th. 7, negative 4, 1. And again, adding all these up, we get the vector negative 7, 11, negative 7, 11, and 21 over 11. And as before, I'm going to scale it. I'm going to multiply by 11 over 7 to eliminate the fraction. And there's also a factor of 3 here. So my scaled U3 is going to be the vector -1, -1, 3. Okay, so through the Gram-Schmidt procedure, my new orthogonal set is going to be T equals to the set 1, 2, 1, 7, -4, 1, and excuse me, -1, -1, 3. So now we have this set, and it is orthogonal. All right, and just so here, looking at what we just did, what the process just created here. So you see, here's my initial set of vectors, v1, v2, v3. All right, and what this process does, all right, so here, u1 is the same, so that one is unchanged, but I switch out v2 for u2. All right, you see, you can kind of see there, and we can confirm through doing our own calculations of the inner product, but they're orthogonal here. And then we switch out v3 with u3. And you see here, right, what that subtraction does, right? It subtracts stuff that's going in the direction of the other vectors in the set to force them, right, or creating them to be orthogonal. Right, now they're not orthonormal. If I do want to make a step further and make these orthonormal, right, then I will take the norm of each one of these, right? So if this is the norm of u1, would be the square root of 1 squared plus 2 squared plus 1, which is root 6. Norm of u2, square root of 7 squared plus 4 squared plus 1 squared. So that's what, 49 plus 16. So that's 49, 66. And then lastly, the norm of u3 is root of -1 squared plus -1 squared plus 3 squared. 9, 10, 11. Okay, so then our new set, call it set W, would be the set where we have 1 over root 6, 2 over root 6, and then 1 over root 6. And then the other one would be 7 over root 66, -4 over square root 66, and then 1 over square root 66. And the last vector would be -1 root 11, -1 root 11, and then root 3 over root 11. All right, so now this set has the additional benefit of not just being orthogonal, but orthonormal. Okay, the length of each one of those is 1. Okay, so again, this very calculation intensive. All right, right here, just keeping organized should be nothing too major.